Good afternoon. Last official lecture. Aren't you glad? Don't applaud. Okay. So next week is just review, and on Friday is a lecture about Berkeley and the actinides, where I would love to see you all. I also like to see you in review. I say 9 o'clock and 1 o'clock. 1 o'clock will be even webcast, but no more eye clickers. Today the last use of eye clickers, okay? What you hear here is subject of our... Can you hear that? Somebody is calling from Mars. Every time you hear this, there's a radioactive decay hitting this little counter. So we will talk about radioactivity today, all right? And this is natural radioactivity that you hear. So we are bombarded by radioactivity. See that little tiny little counter? We will show it to you later. And this is about this big, and this many decays happen on the surface of this coming through the air, all right? So let's talk about this a little bit more. Oh, I want to say one thing. Last time, one of your colleagues said to me, you know, this redox thing, redox equilibria, is just like acid-base. Of course, one could make this analogy, but be very careful. Acid-base reactions are not redox reactions. There is no change in oxidation state. Remember that, okay? All right, good. So, radiation, we know particles and waves, and radiation can be both. Can be particles and can be waves. And if we have non-ionizing radiation, this is infrared, microwave, radio, NMR, MRI, they're non-ionizing, so they're not that harmful. It starts with visible, with UV actually, with X-rays, and with gamma rays. Gamma rays are essentially photons. X-rays are photons of a higher energy. Gamma rays have a higher energy. This is 10 to the minus 16 millihertz here, and X-rays have about 10 to the minus 10. So gamma rays are actually not particles. Insofar, they are particles because they act as photons, okay? But they are actually waves. They are not corpuscular radiation, all right? What is corpuscular radiation? We'll talk about this in a second. So this is ionizing radiation. That means it can ionize chemical substances, can ionize your cell, can damage your cells, and of course you have a very good cell repair mechanism in your body, and some people says even you need to be a little stimulated by ionizing radiation in order to get the repair mechanism constantly going. So we need to have some repair mechanism because obviously we are subjected to radiation constantly. And this is not coming from anything outside, that comes from space and from the soil here and from our environment. And this is not the environment we created, it's the natural environment. So radiation is omnipresent, okay? You're going to be zapped at the moment many times, every time you do. You also have radiation in your body. When you eat, a banana has radiation in there. Please don't stop eating bananas. There's potassium in there. It's very good for you, potassium, if you do lots of sports, and good for your heart. But potassium has one radioactive nuclide in there, which is potassium 40. It has a very small amount, but it's radioactive. And so you are radioactive, essentially. And never mind, I can talk about all kinds of things. So this is waves. So gammas are obviously waves or photons. You could look at this as photons. And then there's particle radiation. So you have the nucleus is made out of protons and neutrons. Okay, we know that. Protons and neutrons. Not every nucleus is made out of protons and neutrons. Which is the nucleus that's not made out of protons and neutrons? Combination of them. Which is it? Hydrogen. It's only made out of protons. But if I have deuterium, you have a proton and a neutron. Then you have heavy hydrogen. And you have very heavy hydrogen, you have two neutrons and one proton. This is called tritium, okay? Especially in molecular and cell biology, you will use this in the biochemistry. So the radiation comes out of the nucleus, okay? Comes out of the nucleus, and you can have several different things coming out of the nucleus. One could be and an alpha radiation. And radiation was discovered the first time around 1898 in the century before last century. And this was discovered by Marie and Pierre Curie and Henri Becquerel. And they won the Nobel Prize for this in 1903, the Nobel Prize for Physics. All right? And then there was this guy Rutherford. He came from New Zealand, and he was in Cambridge and all kinds of different universities. And he worked a lot with radiation and tried to find out what is that radiation. They didn't know much about the nucleus at all at the time. They barely knew about the electrons. Actually, they didn't know much about the electrons at the time. And so he says, okay, there come these particles out there, and I call it Greek alphabet, I call it alpha radiation. That's all. That's the first one, okay? Alpha radiation. And alpha radiation are nothing but helium nuclei. Helium nuclei, okay? That means helium is element number 2 and has 2 protons and 2 neutrons, and they are, the nuclei are positively charged because they don't have electrons. And so the nucleus spits out this helium particle because it's unstable. And alpha decay only happens with elements that are above bismuth, so very heavy elements above element number 83. Or 83 does it already, but 83 somewhere above. So there you have alpha decay. And then there's other decay. So this you can stop by paper, and I will demonstrate this to you. Then you have beta minus decay. There's an electron coming out of the nucleus. The nucleus spits out an electron to get more stable. And that electron has, of course, a negative charge. And this is called beta radiation. Alpha, beta. That's the second one they identified. They say that's beta radiation. And this is beta minus radiation. Because the other possibility that the nucleus can spit out a beta plus particle. What would that be? A positive electron would be a positron. Instead of having a charge of -1, it has a charge of +1. Okay? And we call this a beta plus particle. And this can be stopped by skin and clothing. So let me introduce you to some of the radiations that I have mentioned here. And let me give you this screen here first. Okay, now I can take this off here. So I have, what you hear here is a Geiger counter. And you will see this very soon in the picture above you. A Geiger counter. Is that the picture above? There it is. Yeah. Also, I have a different one here. Okay. Good. So I have to look up there. Ah, thank you. Thank you. Okay. Good. I would like to have this on the monitor too, but that's a different story. Excellent. Excellent. Thank you. So I have here a piece of, what is it, ceramic. See that? That's nice and orange. That used to be called Fiesta ware. It was very popular in the 50s and the 60s here, had this beautiful color, pop art, okay? And so people, they had plates and cups and a whole dinner service or a breakfast service made out of this stuff. And they also had tiles in their bathroom. And this is radioactive. It's uranium oxide. It's radioactive, so it's not going to hurt me, but when you eat on it, there will be some of the radioactivity activity slowly getting into your body, which is not very good. If you have it tiled in the bathroom, people at the old times, they weren't that often in the bathroom. It was not like a spa, okay? So people, they went to the bathroom and came back out, and that was it. Took a shower once a week, whether they needed it or not, and that was it, okay? And so let me put this here on this Geiger counter. This is a Geiger. You see the scale here? This is the Geiger counter. And now we need to listen to it. Can you hear it? No? You can't hear it? And you can see it. You can see how it's pegging here? Let me do it. Okay. So this is obviously, the Geiger counter is sensitive to beta and gamma radiation. Okay? Beta radiation, you can take a piece of plexiglass here, and I put it in between, and most of it is gone. See that? It's absorbed by plexiglass, beta radiation. So you see in these labs where they use tritium and they use other beta emitters, they have these plexiglass shielding around them that they do not expose themselves to the radiation. See the difference here? And so if you have gamma, if I put a piece of lead over it too, a piece of lead under it, it should make a difference. I doubt it that it makes a big difference. Not much. Okay, the lead is not thick enough. So the gamma, so we have a mixed source. We have beta radiation and we have gamma radiation, and there's also alpha radiation, but this doesn't detect alpha radiation. So now I'm going to take a pure beta emitter. You see that this is strontium-90, which has a half-life of 20 years. That means in 200 years, it's totally gone. There's 1 in 1,000 left. And so, see the difference? So we have background now.